Assalamu alaikum students and welcome to another lecture of Slate. This is me, Khawaja Yasin. Let's study chemistry. In the previous lectures, we talked about the atomic structure, chapter number 1 of AS level chemistry, where the concepts were mostly basic apart from the electronic configuration, which was one step ahead from your O-levels knowledge. But now, let's talk about the most important concept of the first chapter of AS level chemistry. A concept, a topic that has to come in your CIE. I repeat, it will be there in your CIE P2 and P1 exam as well. The topic of ionization energy. This is a very important topic. As the name indicates, ionization energy, making ions. That's what we know about ionization energy. We will study that how ions are formed from an atom. So at first, these are the learning outcomes that we need to cater to while studying this topic. Define and use the term of first ionization energy, construct equations, which we will, identify and explain the trends. Trends are very, very, very important. Identify and explain the variation in successive ionization energies of element. Very important again. Understand the ionization energies are due to the attraction between nucleus and outer electrons. We will study then the factors and deduce the electronic configuration of elements using successive ionization energy data. Now, we'll just start off with this topic by just first defining what ionization energy is. In easy words, I would just write for ionization energy, the energy required to remove an electron. Now, what do you need to notice? The definition that I've written, this is not the definition on which you can score well, but this is for you to understand that what exactly is ionization energy. Then we will write the proper definition. But here you need to notice a few things. This is the energy required, just required, not an energy change. And to remove an electron, one electron at a time. So on this basis, let's define the first ionization energy. Now, when we talk about the first ionization energy, the definition will be somewhat similar to what we wrote at the top. The first ionization energy is the energy required to remove 1 mole of an electron or 1 electron from 1 mole of a gaseous atom. This is important. Gaseous atom. To make 1 mole of a mono positive ion. Obviously, if you remove 1 electron, it will become a monopositive ion. Now, what is the most important part? 1 mole of electron, which means 1 electron is removed from 1 mole of a gaseous atom to make 1 mole of a monopositive ion. Now, let's draft a random equation out of it. If X is my atom, the state is gaseous. X will form X positive ion plus 1 electron. Now, X can be any element. I repeat, for now, for AS, S can be any element. In A2, we are going to separate it out. But know one thing, we can remove electron from any element. We know that removing electron will make it a monopositive ion. But even the negative ions, for example, oxides, fluorides, we can remove their electron as well if we apply some force. So if we take the example of, for instance, sodium. Though sodium is solid, but here we have to have sodium in the gaseous state. Why gaseous? What happens to sodium? For that, you need to look at the lecture of A2 chemistry of chemical energetics. That's the concept of A2 chemistry. For now, sodium needs to be a gaseous atom, not an ion. And that would make it sodium positive plus electron. Even I can do that with oxygen, for instance. Although we know that oxygen makes an anion. Let me show you something else. I can even remove an electron from a noble gas, but obviously I would need a lot of energy. So, by this, what I'm trying to tell you is that we can remove electron whenever we want. All we need is energy. So that is what we know. But this is the first ionization energy. That one electron is removed from a gaseous atom to make a monopositive ion. Now, when you have to remove the second electron, you need another ionization energy. You cannot do that कि एक ही दफा you can remove two electrons. One electron at a time. I would write it here. One electron at a time. That is the gist of ionization energy. So what would be the second ionization energy? Second ionization energy, it is somewhat the same definition with a few changes. So if I have to define the second ionization energy is again the energy required. The energy is still required to remove 1 mole of electron. As I said, 1 electron at a time from 1 mole of a monopositive ion. That's the difference. This time it's not the gaseous atom because you made a monopositive ion from the gaseous atom in first ionization energy. So 1 mole of a monopositive ion to make 1 mole of a dipositive ion, because this time you removed an other electron from it. And if we talk about these ones, let's say we have the same ones. What will we do now? Obviously, we will start off with ions this time. And now they would make dipositive ions, and at this time again, 1 mole of electron is removed. So that is what we know is about these ionization energies. 1 electron at a time. So this is the second ionization energy where you will remove the second electron and you will get a dipositive ion. For instance, third ionization energy, fourth ionization energy, so on and so forth. But 1 electron at a time. So this, now we know that if I talk about the standard enthalpy change of ionization energy, this is a positive value. Why positive? Because it's endothermic. Why endothermic? Because energy is required. That's one thing. Now, students, Let me show you one more thing. Now we have a crisis here. Not a crisis, a concept actually. First ionization energy, second ionization energy, third ionization energy, and so on and so forth. Now, which ionization energy will be more than the other, or are they all equal? Because let's first look at the concept. We are removing one electron at one time from the same element. So apparently, it's the same element, it's one electron at a time. They can be equal, they better be equal, but no. Before we understand the concept, let's take magnesium here. Magnesium is normally +2, but we can make it as much as we want. So magnesium gaseous will make magnesium ion gaseous plus electron. Further, magnesium ion will make magnesium dipositive ion with another electron. Then magnesium dipositive is going to make magnesium tripositive with another electron. So it will keep on going. Now let me make the electronic configuration of magnesium here. That's the magnesium nucleus, for instance. First shell, second shell, so these are the three shells of magnesium. Let's draw the electrons. First shell 2, the next will have 8, and then this. Let me draw magnesium here for you, write it for you. 1s2, 2s2, 2p6, and then 3s2. That's magnesium. So we just used energy to remove one electron. This electron is removed. What has it now become? Magnesium positive. So let's talk about magnesium atom first. Here, this magnesium atom has 12 protons, and those 12 protons are attracting 12 electrons. So now there is an equal number of protons attracting an equal number of electrons. There is an attraction. But now, if I have removed one electron, which is now I have 12 protons versus 11 electrons. And they're not competing against each other, they're attracting each other. So now, having more protons will cause more nuclear charge on the electrons. Obviously, at first, there were 12 electrons attracting or holding 12 electrons. 12 protons were holding 12 electrons. Now, these are 12 protons and they are holding 11 electrons. The grip is stronger. This time it has a stronger grip. This won't let the electrons leave easily. So what do you think? Now it is easier to remove the electrons, or is it difficult to remove the electrons? We need more energy to remove the 11th electron now. Because now there were more protons attracting more electrons. So we know that second ionization energy is more than the first ionization energy. And so on and so forth. The number of protons will remain the same, but electrons will start decreasing. And more nuclear charge on those electrons, hence more is the attraction and more energy is required to remove them. Now that's one thing. Look at this now. What has happened here? I removed 2 electrons from magnesium. What do we remember from this? This is a noble gas configuration. In the last lecture, we talked about Why do atoms make ions? To attain the noble gas configuration. And we just got it. So it is definitely difficult to remove electrons from the noble gas configuration. So in that case, the third ionization energy of magnesium, not for every other one, will not just be higher, will be too much higher than magnesium. So that we know that every successive ionization energy will increase. The ionization energy values will keep on increasing. And we can even guess or calculate the group number on the basis of the ionization energy values, which we will just look in a while. So now we have constructed the first, second, and subsequent ionization energies. Identify the trends across the period and in a group of periodic table. Now this is very important. Trends of ionization energy. Trends in the periodic table. In order to study the trends, there are three factors at play. Factors on which the ionization energy depends upon. There are three factors. Number one, this is nuclear charge. Number two, shielding effect. And number three, atomic or ionic radius. Now, what is nuclear charge? We just talked about it. Charge. This is the positive charge by the nucleus on the electrons, holding them. It holds it. So nuclear charge holds the electrons. And what is nuclear charge dependent upon? Since it's a positive charge, it depends upon the number of protons. That's one thing. Shielding effect. It's a different concept. It's a new one. So let's look at this magnesium again. I will draw the outermost shell again. So this is magnesium. And I would compare magnesium with, let's say, let's take beryllium. So beryllium has an electronic configuration of 1s2, 2s2, the same period as that of magnesium, a group 2. Now let's compare these two. Shielding effect. First, let me write what shielding effect is. The effect caused by the inner laying electrons. By inner laying is the electrons in the inner shells. What do? They block the nuclear charge on the valence electrons. Block, or the term is shield. Now let's look at them. These two examples. In beryllium, for example, if this is the nuclear charge on beryllium, These are the number of electrons. We know that beryllium omits its nuclear charge, for instance. So there is less blocking, less shielding by the inner laying electrons. But in the case of magnesium, they are shielded by the more inner shells. The more the number of shells, more is the shielding. Shielding is like they block the passage. For example, if this mic is in between and I am throwing out some ray from me, what will happen? This will block the throw. If there is a tube, you just light a tube, this will block it. This will shield it. So that is what the shielding effect is all about. So now the way nuclear charge depends on protons, shielding effect depends on the number of shells, inner laying shells. Atomic radius, we know it's about the radius. Now, why atomic or ionic radius? Atomic radius is when we talk about the first ionization energy, because in that case, we're dealing with the gaseous atom. But the subsequent ionization energies, we talk about ionic radius. Now, what happens? If the radius is increasing, let's look at this one again. Now, beryllium has a smaller radius than magnesium. So, beryllium will hold its valence electron strongly than magnesium. So, that is the case. In the case of magnesium, since it has a huge radius than beryllium, so magnesium will have a lesser hold on its outermost electrons and beryllium will have more hold. So if beryllium has more hold, it will be difficult to remove electrons. And when magnesium has lesser hold, it's easier. So let's understand by the proportionality concept. With atomic radius, more the atomic radius, lesser the energy required to remove. So this is inversely proportional. More the radius, lesser is the energy required. Nuclear charge. More the nuclear charge, so the nuclear charge on the outermost electron is more. It is difficult to remove the electron. So this is directly proportional. More the nuclear charge, more the ionization energy. Shielding effect. More the shielding, lesser is the nuclear charge going towards the outermost electron, and they are less bound with the nucleus. So it's easier to remove the electron. So more the shielding, lesser the ionization energy. Now, last thing about today's lecture, we are going to talk about the trends across the period and trend in a group. Trend in a group, trend across the period. So let's first talk about trends across the period. By across, we always mean left to right. Now, if we have an example, sodium. Let's look at okay. We have still one more left, but let's see. So this is sodium. In this case, this is sodium, magnesium, aluminum, silicon, phosphorus, and sulfur. Now, that is what we have. In this case, sodium, magnesium, aluminum, silicon, phosphorus, and sulfur. we need to understand the trends here. How does a period affect it? Across the period from sodium to sulfur, let's study about it. In the case of sodium, we need to remove electrons. And there are three factors to study. These are the factors: nuclear charge, shielding effect, atomic radius. So across the period, nuclear charge increases because the number of protons are increasing from sodium to magnesium to aluminum. Then shielding effect, it remains the same. The shielding remains the same. Why? Shielding effect is unchanged because all elements in one period have the same inner laying shells. ये देखो, 1 2 1 2 2 complete shells in period 3. So the shielding effect remains unchanged. And the radius across the period, it decreases because there is a stronger attraction. Here we have 11 proton versus 11 electron, and here I would say we have 14 electron versus 14 protons. More attraction, more tightly towards each other, and that makes it a little smaller. So atomic radius decreases. This is the concept of inorganic chemistry, which we will discuss in detail there. But if we talk about these three factors, if the nuclear charge is increasing, ionization energy increasing. If shielding effect is unchanged, so let's not talk about it, but you can mention it. Radius is decreasing, so ionization energy, as being inversely proportional, it's increasing. Hence, across the period, ionization energy increases. That's the rule. And lastly, down the group, it's very easy. Down the group is basic. Like if we have sodium, first lithium, I mean. Lithium, sodium, potassium, so in this case, we know that down the group radius is increasing. So let's talk about these. There are two factors at play. Down the group, radius increases, and down the group, shielding effect increases. Why does it increase? Because more inner laying shells are being added. More the shells, more the shielding. And radius is also increasing. And yes, unfortunately, the nuclear charge also increases. But we don't normally talk about it. Because if I talk about nuclear charge, so that is cancelled by shielding effect. Because the nuclear charge is increasing, even the shielding is increasing, they both get cancelled out. But still, if the shielding is increasing, so ionization energy, being inversely proportional, decreases. So lesser energy is required. Radius increases. So with radius, even again, it's inversely proportional. It decreases. We will not talk about atomic radius because that goes against the explanation. But these are the trends. So down the group, the ionization energy decreases. Across the period, it increases. Down the group, it decreases. So these are the trends of ionization energy. And they're very important because these three factors at play: nuclear charge, shielding effect, and atomic radius. You have to give your answer according to these three factors, and that is the only way to get the right answer. So that's all for this lecture. In the next lecture, we are going to talk about the successive ionization energies, how to calculate that what is happening, how to know that which element belongs to which particular period. In the next lecture, we are going to talk about that. So thank you so much for being here with me. Take care and Allah Hafiz.